Okay, so one huge idea in this class is there's two sort of numerical statistics kind of questions a person might ask. And one of them, the answer to which is a percentage. So you might say, what percent of people in the United States smoke? Something like that. And so what you're after is a percentage. The parameter in question, you have an assignment question in 9.1 that asks about that. What the parameter in question, what is it this person's trying to figure out? And in the case of the example I just did, oh, it's a percentage. I want to know what percent of people smoke. But the other question is maybe, no, I don't really care about what percent of people smoke. I want to know how many packs of cigarettes a year do people that smoke. Notice the data there is not a percentage, but the data is a number, 27, 85. So there's sort of two types of data. Is the answer to the question at hand a percent, or is the answer to the question at hand a number? Do you see the difference? There's questions in both 9.1 and 9.2 that are kind of confusing in the way that they're worded because they say, what's the parameter of interest here? Well, notice in this question, the person does not want to know a percent. And by the way, does it make sense you could actually make a percent question out of that? So this person did a sample of 5 sea urchins and sat there and counted all their spikes, I guess. Does it make sense you could say what percent of those are over 200 spikes? What percent of sea urchins have more than 200 spikes on them? A person could ask that exact same question with that exact same data, or ask a different question with the exact same data. But this person is asking not a percent question about about sea urchins, but rather just how many spikes do they have? Do you see that as an interesting question? My guess is probably never thought about that before. Can you appreciate somebody that was really into the ocean animals or a marine biologist or something could get totally interested in that? I mean, I don't think I'm interested in that, but I can see, I mean, like I like to stop and just think for a second. I can see how somebody would just think that's totally cool. Do you have something in your life that you find super interesting and you really like to understand all about it? I can see somebody thinking this was kind of interesting. So the point, I guess what I'd really like to get across today is to help you deepen your understanding of this idea of a confidence interval. Why is there such a thing as a confidence interval? I mean, that's the main thing that I want you to get. Let's see if we can make some progress with that. So let's all do this. And I want you to do this too. Let's go into your graphing calculator. And the things that you would want to do with this, if we want to answer the question, how many spikes do sea urchins have? The fact that somebody would have to go count some should make lots of sense to you. Somebody's got to go count them. But the key is you only have one option, and that is to count a sample of them. Do you understand that? You cannot get them all. But you still would like to know the answer. The problem is and you should understand this, if I figure out the mean of that sample, that'd be a pretty decent answer to the question. But notice if you stare at this, your first thought should kind of be, wow, that's quite a bit of variation. For me personally, I wouldn't have been surprised if sea urchins had exactly the same number of spines. Every one of them did, right? Octopus, they all have exactly the same number of legs. But apparently this is a little more random than that because you get quite a bit of variation. So there's a ton of variation there. It looks like the smallest is 175 and this one's almost 300. It's like almost, you know, approaching double as many spines. That's interesting. I wonder if it's like an age thing. I don't know. So anyway, as a statistician, you go into your calculator and say, well, I can handle this. I'll just stick all those numbers into my graphing calculator, 213, 180, 175, 242, and 295. So you got them all in there. And then you go to stat, but this time over to calculate, and you do one variable statistics. Notice we're not comparing the weight of a sea urchin to how many spikes it has. We're not comparing the age of a sea urchin to how many spikes it has, because maybe that's the reason. Does that make sense? Maybe old ones have more spikes. I don't know. So this is a one variable test. We're not comparing two things. We're just looking at one variable stats. And there's really two takeaways from this, and one of them is the sample, very important, sample mean, 221. So the point here is, near as you can tell, you should not say sea urchins have 221 spikes, because clearly there's 5 examples right in front of you that that's not true. What do you say with 221? I'm gonna pick on people. Danny, what do you tell people about 221? Exactly. Nice job. Average. Don't say that is how many spikes. That's the average. And that feels right because like there's some less and some more, right? So that kind of feels right on average. But the point is, that's the whole point of statistics. There's a ton of variation there, and good, because that makes life interesting, I think. So on average, it's 221. But the second thing you should think is that's probably not true. And that's the whole point of what we've been doing lately. That's just a sample. And not only that, it's a really small sample. So what we've been learning lately is when you take a sample, that's just one answer. But even if you just went and got 5 more sea urchins and counted them, you're probably not going to get 221 even yourself in the same exact pond, right? So we understand there's a lot of variation to that. And so it could be that you happen to sample some really low spiked number. And so the average could be 300 and you just got a really bad batch, right? Or maybe it's the opposite. Maybe you got a batch that's really old and that's lots of spines, and the real population is actually only 180 or something like that. Do you understand that cool, but not equal to the actual answer? Do you understand that nobody wants to know 221? Because it's not even true. That's just like your dumb little study. Nobody cares about your dumb little study. They actually want to know the answer. Like, isn't that what this person's asking? I want to know how many spikes they have. And so it does make sense to go do a sample. And I don't know about you, but if I made it to 5, I'd be like, I think I'm tired of counting now. I think I'm going to have to quit. I can't do this anymore. I can see why they might have quit at 5. So I don't really have a choice if I want to answer this question, unless of course some nerd's already done it and I can go on Google, right? But somebody had to be first. That's the idea of this class. Maybe this is a question nobody's asked before. So what you've got to get is that these two things are not going to be the same. That's the whole point. You should already know this, but I'm just kind of reinforcing the idea of a confidence interval. This is a sample, and we know that those samples are normally distributed. And so that could be really low, could be really high. That's the whole idea of a confidence interval, is to go one step beyond this and actually calculate the error and then report back that although 221 is the best answer I got, the real answer, notice in this case, the error is not a percentage, it's a number. Like what if the error here was like 50 spikes? If the error was 50 spikes and you said, I'm fairly confident the right answer to this is within 50 of 221. So it could be low, 170, it could be high, 270, but I'm pretty confident it's within 50 of that. The right answer is within 50 of that. That's what we've been doing recently. We know that this answer is not right. So we go one step further and produce an error. And then we can actually say, okay, well, I know the right answer is probably somewhere in here. That's the idea of a confidence interval, sort of intellectually honest. If you actually want to know the answer to this question, although you can't report this is the answer, you can at least say it's within this range. That's the idea. Okay, how do we do this? How do we find a confidence interval? Again, in the real world, you get to decide how confident do you want to be. If you decide, I love sea urchins, they're my life, I need to be really confident. I want to be 99% sure that I'm right about this. Does it make sense that's going to make your error really large? Please think this through with me, because you have some random questions in your assignment that kind of ask about this. But if you decide you want to be really sure that the right answer is between these two values, then you're going to have more error. If you say, it's only a sea urchin, I'm just mildly curious about this, so I'm 70% confident it's fine, well, then you might have less error. So you get to decide how confident do you want to be in the real world. On the homework and in this class, I'll be telling you, but let's make, I don't know, 90%. So I'll add that to this. Boom, 90%. Let's make a 90% confidence interval. Now, you already understand this, because what we really need to do then is find an error. But as I said, notice in this case, the error is going to be a number because the parameter, the thing we're talking about, is a number. We got to go find out what that error is, and it'll be something in spikes. It'll be 20 or 80 or something like that. But this is actually all you need to know. Now, in previous sections, did we not do this? Once somebody said they wanted to be 90% confident, didn't we go get a z-score? So we said, what is the z-score that's associated with that 90%? So we said, okay, cool, let's go get that. Second, and we went down here to inverse normal, which produced a z-score for us. And because I said 90%, the area left of the z-score location is 95. I'm not going to repeat that right now or reiterate that. So I got 1.64 for that. So we went inverse normal 0.9501. And we got approximately 1.64. And then you may remember that, where did my note sheet go? Must be here. You might remember that then we, at least in the last section, we took our z-score and we multiplied it by a standard deviation. Remember, that was the calculation for a standard deviation of sample proportions. That was the calculation for that. Well, notice in this section, we're doing the same thing. So this is on your note sheet. We're taking the z-score, which I've covered up right now for a reason, and we're multiplying it by the standard deviation. But notice when the standard deviation is a mean, a sample mean, we have a different way to calculate that. It wasn't PQ over N like we've been doing in 9.1. It was the actual standard deviation divided by the square root of N. So that's the second thing we have to calculate. And then we're going to get our error just like we did up here by multiplying those together. But what I'd like you to stare at right here for just a second is just how similar these two formulas are. Like in 9.1, this should be a little bit in your concept that the population proportion will be somewhere between these two errors. Well, isn't this exactly the same formula? The actual population mean will be somewhere between these two errors. And you get that error by multiplying a z-score times the standard deviation, a z-score times the standard deviation. I mean, that's the idea. Now, it turns out though, and this is on the bottom of my sheet here, but it turns out that there's some history here that I'm not going to go into much detail about, but there was a person named Gossett in 1908 that supposedly worked for a beer company. I think it's one in Ireland, the dark stuff that is gross. Guinness. Worked for Guinness, and what this person noticed is if you have a really small sample like this, if you have a really small sample, then it wasn't modeling the real world very well. This is what he noticed. And so he ended up creating something called a t-distribution, ultimately something called a student t-distribution. And there's, again, some history there as to why it's called that. But I wrote on the board already something I'd like you to understand. You're already comfortable with the idea of a normal distribution. Normal distributions are bell-shaped. A t-distribution is also bell-shaped, but the difference with a t-distribution, there's a little bit more room for error in it. In other words, what's the difference? It's still bell-shaped, but does it make sense? The percent in the tail's a little bigger and it's not quite so tall. So more of the area is in the tails, more, maybe I'll say it that way, more area in the tails. And basically he discovered that did a better job of modeling things. And the problem here is exactly what we're finding, which is if you want to know how many spikes are on a sea urchin, you got to count a lot of spikes, and you might want to stop at 5 because you're tired. And so what he found was, and you can appreciate, you know, if we answered the question 221 based on our small sample, the question is, did it turn out to be right? If somebody went, if you had a bunch of graduate students and they all went out and counted a bunch of sea urchins and so forth, and you found out, wow, 221 wasn't right. He basically discovered it wasn't working very good. A normal distribution, we went inverse normal to get a z-score. He basically found out that 1.64 number wasn't working. So he invented something called the t-distribution. Let's see. How many of you have 83? It seemed like that was nobody in this class. Everybody has 84s in here? That's true. So it turns out we don't actually use a z-score. You may look at your chart now. I was trying to cover this up a little bit earlier. Notice what's different about this. We used the z-score because the percents were normally distributed, but for means, we're using a t-score. Notice it's the same exact syntax or the same idea. It's just not, we're not using z-scores, which came from normal distributions. We're just using a different kind of button on the calculator, if you will, or a different equation. It still has that normal shape. The area under it's still 100% or 1, but it's just going to give us a different answer for this. And what it's going to give us is actually an answer that's bigger than this. It's going to give us a bigger answer than this. As I said, he discovered it wasn't working for something he was calculating in the beer company. So instead of that, we're going to do the same thing, but we're going to use a t-score. So I want to show you how to do that. It's really easy. Guess what? Instead of inverse normal, it's inverse t. Pretty easy to find on your calculator because it's right next to where you just were. We just went to inverse normal. It's right below it, inverse t. But it actually asks some weird questions. Did you notice a second ago when we did inverse normal, it wanted to know the area to the left? And then we always put in 0 and 1 for the mean and the standard deviation. But notice it actually asked for some kind of weird information here. In my calculator anyway, yours might not ask for anything. You have to kind of read your note sheet, which I'll show you in a second. Actually, I'll show it to you right now. It actually asks for the area to the left, just like inverse normal did, area to the left. But then instead of the mean and the standard deviation, it asks for DF. What the heck is that? DF? So that hasn't changed. That's still 0.95. But what's this DF thing? This is degrees of freedom. DF, degree freedom. Freedom. And it turns out that's just n-1. Now, you've actually seen this before. I don't have this up or in front of me. But do you remember when we found a sample standard deviation before? How we divided not by n, but by n-1? That was on the first test, so it's kind of on an old note sheet. But we divided by n-1. That's the same language, actually, and that's what we're doing here. In other words, if n, which for us was 5, then we're going to put in n-1, we're going to put in 4. The basic idea, I won't belabor this point. However, I will say this. I did send you guys an email the other day because this little sea urchin idea, I was kind of surfing around on Google, just kind of seeing, can I learn anything more about some of the things I'm teaching? And I was kind of looking into chapter 10 a little bit. And I found a website of a guy that really does a good job. And then I emailed his YouTube channel to you. Fantastic, really good explanation. So if you're more curious about this than what I'm about to say, you're more than welcome to go look into it. Because he talks about this, but The main idea is this: what if you wanted to know how many spikes are on a sea urchin? So you just grabbed one and counted them up, and then you said, "I'm done. I got one answer." So let's say that was like 400. And that's why you quit, because there were so many of them. Like, I can't do that again. Oh, it's around 400. That's interesting. I wonder if other ones. And you just thought to yourself, I wonder if there's a variation from this class. I wonder if other ones all have, if they all 400, like octopus have 8 legs, or is it a little bit of variation, like they're between 405 and 395, or is there tons of variation? I don't know. That's interesting. Again, if you're a biology person, you might genuinely find it interesting. But does it make sense if you got 400, you counted them up and got 400, does it make sense you have 0 freedom as to what the right answer to that question is? How many do they have? Well, I guess 400, because that's the only, n is 1. So I have no freedom as to what I think the answer is. Do you understand what I mean by that? It's got to be 400. That's the idea behind degrees of freedom. If there's only 1 sea urchin, you have no freedom. If you have 2 sea urchins, then you have 1 degree of freedom. And that second sea urchin would actually tell you a lot, because if the second one was 399, then you would kind of think, oh, they're actually 400 is pretty close, and there's not much variation. They're all right around. That would be your conclusion. Whereas if the second one was like 208, then you'd be like, what? 400 and 208? What's going on here? Like, what's happening? So you have that 1 degree of freedom you had by having one extra sea urchin kind of told you a lot of things. That's just the rough logic as to what this means. So it just means n minus 1. So, okay, great. Well, let's go do that. So I type in areas 0.95. I say I have 4 degrees of freedom since as I said, n is 5. I'll write that up here. N is 5. And what it's going to give me is, well, kind of like a z-score. It's just going to give me a z-score, but it's off of a slightly different distribution. And for that reason, make sure you're getting the same answer I get. You get a bigger number for this. In other words, you're further out there is the idea. So in other words, in this section, we're not going to be using a normal distribution to produce this answer. We're going to be using something called the t-distribution. And as a side note, I mean, isn't that kind of cool that somebody, I don't know, realized it wasn't working, and instead of going, wow, this isn't working, like sat there and figured out some other way to do it. I mean, it's hard enough just to learn, right? But that person invented this in 1908. They didn't even have a graphing calculator. I mean, I just find myself going, man, that's just cool. And I am curious about the history of that a little bit. Probably not curious enough to go look into it, because I'd rather ride my mountain bike. But that's pretty amazing that this person came up with some other, and I did show you the equation for a normal distribution. It was a pretty complicated equation, wasn't it? And the one for this one is even worse, and it's way worse. So pretty cool, and basically found, hey, this actually models, and the basic idea was it does a good job of modeling or predicting if your sample size is really small. That's the idea. Go ahead.
The n is the number, is that like the number of samples?
That's the number of the sample. In other words, hey, I checked with 5 people, therefore the degrees of freedom is always 1 less than that.
Oh, I thought it was 5 minus 1. So 1 less than 5 is 4, right?
Yep. So that's why I put 4 in there. So this is kind of our z-score, if you will, in this section. Yeah, it's just a z-score, but using a mathematically slightly different bell curve. They're both bell curves. This one's got bigger tails, so it does a better job with small sample sizes. So it's just a z-score. I mean, I guess I'm calling it's a t-score, but it's the same thing. But so notice the second thing I've got to calculate is to multiply by, just like here, I took the z-score times the standard deviation. I got to do the same thing here. But notice what this is asking for ingredients. I need to know n. I know n, it's 5. But I also need to know s. What is s on your note sheet? That's your sample standard deviation. In other words, when you made this calculation earlier, when we said stat, and we went over to 1 variable statistics, remember in the real world, it's great to write down 221, but it's actually, you almost would never just want to write 221 down. You'd also want to write down 49.4, just because remember, just like my example a second ago, if the first one was 400 and the second was 399, you're like, oh, there's not much variation. They're all about 400. Whereas if the first one was 400 and the second one was 205 or something, it's like, whoa, that's a lot of variation. Well, notice this is telling us it's not weird to vary by 49 spikes. And so, wow, sea urchins are all over the place. And because the sample size is so small, you can, I'm not saying you can see 45, see 49 there, but you can see there's a lot of variation, right? You should not be surprised the standard deviation wasn't 4 or something like that. So my point is, clear back at the start when I had all that up, I should have also calculated and again, you have a choice as to how to round that. I don't care as far as the test is concerned. But remember, as a rule of thumb, you carry it 1 decimal place further than the data. So we're told in this section that the error requires a t-score to be multiplied by the standard deviation. So I need both of those. And so, okay, what's this guy then? Well, I guess that'd be 49.4 divided by the square root of, not n minus 1, just n. So I get, again, round it however you want. I'm going to call it 22.1. Now, before I cross the finish line there, I just want to show you something kind of interesting. A second ago, we did inverse normal and we got 1.64 for our sort of our z-score. Whereas with a sample of only 4, or I'm sorry, a sample of 5, we sort of had a higher answer for this. And as I said before, the logic of this is if you only check with 5, then you should expect that to be kind of bad. And keep in mind, if you have 1 sea urchin that is weird, that's going to have a huge effect because in 5 sea urchins, that sea urchin's 20%. They're 1 out of 5. They're making a big difference. But does it make sense if you checked with 80 sea urchins? Now 1 weird sea urchin is going to get normalized by 79 other ones, and it won't be as much of a problem. So I just want to show you this real quick. So we said, okay, let's do inverse t, same area, and we did it with 4 degrees of freedom, and we got that second answer. But what if you had not checked with 4 sea urchins, but had checked with, say, 14 of them? Notice the error gets quite a bit smaller, like it's not as strange, because you can sort of count on 15, and so notice n is 15, so degrees of freedom would be 14. 15 sea urchins, there's not, you're more likely to be right because you actually counted quite a few sea urchins. What if you went clear up to 90 sea urchins, and so this would be 89? What do you notice about that number right there? Do you notice it's actually getting pretty close to this one? It's like what this distribution was invented for, as I said, is for really small samples. But if the sample's big, they're actually the same. So what if I went way up to 212 sea urchins? I can't imagine counting that many of them. So this would be 211. Remember that number, 164, 1.64. Notice, like, see how close it's getting? So the more and more you check with, it actually becomes normal. So this is kind of an important idea. So we use this. The point of this is we use it when the sample size is small. So the point here is if you had checked with 212 sea urchins, these two answers are pretty much the same and it sort of wouldn't have mattered. You see what I'm saying? Okay, so let's cross the finish line then. Exactly. So just like in the last section, I took the z-score times the standard deviation. I'm going to do the same thing here. So Error is my z-score, well, my t-score of 2.13 multiplied by my standard deviation of 22.1. And notice roughly in your head, 22 times 2 is like 44. But it's going to be a little more than that. 2.13 times 22.1, 47. So approximately 47. The question is, do you understand the value of that calculation? Do you understand? It's like, hey, that's really cool now. Because what you're saying now is you're admitting, I don't know the right answer to this question. And so my best guess is 221, but I was really lazy and only asked 5 sea urchins how many spikes they had. But then I did this kind of cool math calculation that is insanely complicated. I mean, ultimately, it's a really crazy calculation. And I basically found that there's an error of potentially 47 from 221. This is what a confidence interval is. So I could say 221 plus or minus 47. Thank you. The real population mean is, well, I guess you could say 90%. There's a 90% chance that the real population mean is somewhere between here. It's in that range. It's 221, but there's an error of 47 spikes in my study. Maybe, as we've said before, a better way to say this is to go ahead and add 221 plus 47, oops, and get 268, and 221 minus 47 and get 174. Again, I part of me wants to say I think that answer is better, but that's an opinion. That's not true. So if you understand the concept of a confidence interval, then when you get 221, you should almost immediately just erase it, like throw it away. It's wrong. But if you go one step further and you say, okay, based on that calculation, I can actually now say something about the actual right answer. The real question I asked was not how many spikes do a sample of 5 sea urchins have. I want to know how many spikes all sea urchins have. And I can at least now say, I know the answer to that, or at least I'm 90% sure, is somewhere between 174 and 268. You see the logic in that? You see why that's better? I would say this, you know, for most of us, isn't that important of a question. So we're like, oh, okay, that's great. I'm happy with that. I can be happy with that because I'm not that concerned about sea urchins. But we're going to do this again in a second with breaking strengths of ropes and things that kill people if you get them wrong. And, you know, at least then you'll kind of say, oh, okay, I see the logic in that. Now, if you cared a lot about sea urchins, though, I think you should be kind of unsatisfied by how big of a range this is. Do you find yourself thinking, well, I really didn't learn anything about sea urchins because there's like a range of 100 there almost. It's like 100 between these two. And so I'm not really that happy with that amount of error. What I would like you to try to do right now is just to see if you can do this. What if n had been 87? Like you had gotten 221 for your sample mean, but you'd gotten it by actually counting 87 sea urchins. Does it make sense? That's a much more solid number now because you got an average of 221, but you averaged 87 sea urchins to do it. That's a much more solid number. And because of that, that means your 221 is actually, I can count on it a little bit more. Well, what that's going to do is it's going to make the error way less than 47. You're not going to have near as much error. Did you see how many places n was in those previous calculations? Did you notice that it was here in the inverse t, like it was right there? Well, one less than it was there, but then it was also in this calculation right here. It was like in both chunks of it. And so the fact that n is not 5, but 87, it's going to be a way more satisfying answer, I guess you could say. I want to give you a second. Can you redo this calculation? Can you recalc T and then multiply them to get an error? And then when you get that error, do you get something far less than 47? I'll give you a second. Yeah, I didn't change anything else. Still doing 90% confidence interval. We're still saying the sample standard deviation was 49.4. The only thing we changed is that all of that info came from N is 87, not 5. So I'm doing this with you now. So second distribution. So I'm going to go inverse T. The area left of the z-score, the t-score that I'm at is still 0.95, but this time I have one less than 87, 86 degrees of freedom. Notice instead of 2.13, what do I get? Well, as I showed you before, a number much closer to the z-score number. So I get like 1.66. Does it make sense that's going to make the error smaller? Because I'm going to be multiplying by 1.66 here. Again, for this purpose, I don't care how we round. And then if I take the standard deviation, which was 49.4, but I'm dividing not by the square root of only 5, but now 87. Wow, that's huge. Take a look at the difference between those two numbers. Before, and I want you to think about this, before, if I did a sample of 5 sea urchins and I got my answer, and then you did a sample of 5 sea urchins and you got your answer, this right here is saying it wouldn't be weird if our answers were 22 apart from each other. Because remember, 1 sea urchin in 5 makes a big difference. So it wouldn't be weird if yours was different from mine by 22. What is this number saying? 5.3. This is saying if you did a sample of 87 sea urchins and got an average, and I did a sample of 87 sea urchins and got an average, now, because those are so big, it would be weird if we were 5 apart. Now we're going to be really close because 87 is such a huge number. So the standard deviation went way down. So notice when I multiply those, I'm going to get a way smaller error. Both of those numbers were smaller. Again, I don't care about rounding here. 1.66 times 5.3. That's roughly 9. I'm going to round it off. Roughly 9. Wow. You mean now I can say that the mean is 221 plus 9, which is 230, or 221 minus 9, which is 212. Do you agree that sort of that second answer that we got then sort of has a more like if I'm a biologist, I feel like I kind of know the answer now to the question. Now, is it perfect? There's still 9 spikes of error, but notice if I can say it's between 212 and 230, that sort of feels like I know something now, whereas before it kind of felt like I didn't know that much. Again, what I'm trying to get across here is like, I don't want you just to be a button pusher. Like, if you call me over and say, what button do I push to get this to work? That's okay to ask, but I want you to understand conceptually why this is kind of a cool thing and conceptually what it means. Question.
I was just question about, I'm wondering, when you do the list of the values to get the S over that extension, I don't remember how to put that in on the calculator.
Yeah, you're putting it entirely in the stat button. You can do this in Excel or in your calculator, but if you go into stat and you go into edit and you type all of those numbers in, once they're in there, you go back to the stat button, but this time instead of edit, you go over to calculate and it's one variable stats because there's only one variable here. How many spikes do they have? That's it. Yeah, it's always a little bit glary. So stat, there's 2 things you do, edit and calculate. Edit is where you get all the data in there. When you're done getting it in there, then you hit stat, but this time go over to calculate, one variable stats. And notice it says list 1 because that's where all my numbers were. And then it says, okay, great. The 2 things I care about here, there's the average, the mean, and there's the sample standard deviation. Notice I never even talked about the population. You have 5 sea urchins. Should be talking about a population. So the point is, does it make sense that choosing a large sample size? I mean, that's why on your final project, for instance, I said, pick something that's somewhere between 30 and 100 numbers. Notice we just did 87 numbers and we kind of got a satisfying sort of an answer. So if you have a question that you're trying to answer for your final project that involves numbers of something, and again, we're going to play around with this more in the next few days. There's all kinds of number related questions that you might be interested in. How many hours does the average American work per week? How many packs of cigarettes does a smoker smoke? How many miles a day does the average person drive? How many hours of sleep each night does a person get or need? Like, those are interesting questions. And to be able to report not just that you got an average of 221, but that you're actually able to hypothesize that the real answer to the question that you want to know is actually somewhere between 212 and 230. That's pretty cool to be able to say, I think, because that's a pretty tight range. Blake.
So what was the value that you added or subtracted 9 from at the end of the problem?
From the same mean we had before. So I went 221 plus and minus 9 instead of 221 plus and minus 47.
Okay, thank you.
Thank you for asking. Now, all I want to do is just another example of that. So watching you do it once is not the equivalent of understanding it. Like, it takes a little bit of time and thought to make sense of this. Do you have a physical copy already of hand in homework number 4? You may already have, but if you don't, I printed one. Come grab it. Because I actually want to refer to it right now. Because we're about to do a problem that's really similar to that.
When you do the 221 plus or minus 9,
Yeah.
like, is there a formula that says like mean plus or minus something? So
Yep, right there. The mean, the population mean is the sample plus the error, and then the sample minus the error.
Okay, so we're still going to use this one
Yeah.
for these.
Mhm.
So we're using both of them.
Yeah, so if it's actually, I'll say that to everybody. So the big takeaway here, in a sense, is if your data is a percent, If your data is a percent, which means your answer is a P for proportion or percent, P hat is your sample proportion that you got, then your population proportion is the sample plus the error and the sample minus the error. That's the range in which the real lives. This section is exactly the same. This is what we just did. We said, hey, the actual population mean, the right answer for sea urchins. If I took my sample 221 and I added 9, that's the upper end. If I took my sample and subtracted 9, that's my lower end. It's the same exact logic. It's just, is my data a percentage or is it actually a number? So these two sections are not different, I guess is what I'm trying to get across. They're real similar. Now, your project is similar to this. And I said right on here, hey, there's a couple of chapter 9.1 questions I could ask you about this sample of 40 wires that were tested. But then there's also a 9.2, which is what we're doing today, question about it. So I'll allude back to that in just a minute. But what I want to do is a particular question, just like that, right now. So this is just another of the same question we just did. I'm going to turn you loose to take a stab at this and perhaps get it wrong. But let's just stare at this for a second. So spikes on a sea urchin, that would only be interesting to certain people, but breaking strength of rope, that's more important to a lot of people, and people's lives are at stake if you get this wrong. And so you probably don't know this, but if you buy rope, it'll always say on it basically how strong it is. And notice in this case, I'm talking about 6 millimeter rope. And notice right here, this is a chart I just stole off the internet yesterday. And notice up here it says nylon rope. It turns out there's all different kinds of rope. Nylon is like the cheapest, crappiest rope there is. If you want climbing rope, it'll be way better than this rope. But just cheap nylon rope, it says the 6 millimeter rope right here, it says the breaking strength of that is 1,486 pounds. It also tells you what it is in metric kilonewtons if you live in some other country. But the key thing here is this. And so if I bought this rope and I was going to do something with it, I could do something irrelevant, like tie down a load of sticks on the back of my trailer, in which case it breaks. I don't really care so much. But if I'm going to hang off of the ski lift off of it, which I've mentioned I do at Mount Ashland, if I'm going to hang from that, well, now I'm going to check this a little closer, right? Because lives are at stake now. And so notice it says the breaking strength of that is 1,486 pounds. Well, I would hang from that, because I don't weigh anywhere near that. I weigh 1/7 of that. If you take 1,400 divided by 7, you get 200 pounds. So it's like, it could hold 7 of me. So I think I'll trust myself for that. And so off I go. But notice, this is the company guaranteeing this. Does that make sense? How in the world did they get that number? And they're guaranteeing this like they will both kill people and be out of business because of liability lawsuits and stuff. So it's like, you know, they have lots of reasons to not get this wrong. Where did they get that number? I mean, does it make sense that they broke a bunch of ropes? That's what you got to do, but you can't break all the ropes because then you have no ropes to sell. So you break some ropes. And of course, you don't have to have 100 foot of rope and break the whole thing. You need 1 foot and you can just break a foot of it, right? But they got to break a lot of rope and they're not going to do 5, right? They're probably not even going to do 87. They're probably going to do 387 or something like that. They're going to have to kind of be really sure. And that's part of what that homework assignment is about. And that's why this is so important. If you take just a sample of these 7 right here, you're going to get a sample mean. But again, that's wrong. The sample mean is not the real mean. And so you got to know that in the real world. You got to know the real mean is in a range somewhere. Does it make sense in the case of these ropes? You want to pick the lowest one possible if you're going to report how strong something is. So you get ahead of me. Let's do well, this feels more important than sea urchins. So why don't we see if we can produce a 98% confidence interval for this data. Notice There's only 7, which is sort of dangerous. N is 7. This is what your test question is going to look like. I'm not going to say that much. I'm just going to say, here's some data, produce a 98% confidence interval. That's all I'm going to say. And you can round however you want. I could care less. As I said, you're going to get a little frustrated with my open math because if you don't read really carefully about how they said to round, you're going to miss stuff on there. But this is one of the big takeaways of this class. So I'm going to give you a second to see how much of this you can do by yourself before I just answer it. I'm going to give you enough time to maybe type all those numbers into your calculator, and then I'll put our sample problem back up there so you can kind of stare at that. Maybe that helps because I've only shown you this once, right? So you're not very good at it yet. Feel free to talk with your neighbor about this. Feel free to ask me a question. I would rather you get this right under your own power with a little bit of help than just watch me do it. Cool. Also be looking at your note sheet because your note sheet's what you're going to have on the test. So is it speaking to you? Putting our first note back up now because it looks like people aren't looking up there for info anymore in case you want to look up that. Feel free to ask me questions too. the weird thing about this is it's like this. A lot of products comes from, like, you're probably importing stuff. Like, you know, you get strands. You have to test all the time. So I would say just step breaking, especially if it's natural. Some trees are really strong. In case of step breathing. So all the important thing is that you know this and you. Okay, to check your work really quick, just pause 1 second and look up here. I want to make a point as strongly as I can make it. Did you get this? You did not, did you? Now, what I'm worried about on the test is, what if you don't get this right? Because I didn't really do anything other than type the numbers in. But in a room this size, did somebody type them in wrong? That'd be easy to do, isn't it? I want you to take a look, and because that's not what you got, right? You did not get 2166 for your average, for your mean. So I want you just to look at my numbers and tell me, I want you to tell me what pretty understandable dumb mistake I made. This is one of those rare times when I made a mistake on purpose. Usually they're an accident. Yeah, it's 2272, but I accidentally typed 2722, which is an understandable mistake. My question is, on the test, how am I going to know that you did that? The answer is I'm not going to. Like, double check this, because we're using a machine here that does a lot of work for us, which is really wonderful. But everything you're doing, everything you do after this is going to be wrong just because you typed one number wrong. So take 5 seconds and make sure you typed it in right, because it's going to be really hard for me to grade. And I don't want to take points off. If your mistake was dumb, like mine just was, it doesn't mean you don't understand it, but how am I going to know? So hopefully you did get that. And I didn't say anything about rounding. I'm not done letting you think, but I'm going to, because these are whole numbers, I'm just going to use whole numbers for this. I'm going to call that 2102. And my standard deviation, my sample standard deviation is 133.3, I guess. I don't know. Again, I don't care how you round. But hopefully you started doing your calculations using those numbers. I'll give you another couple of minutes. Ask me questions. I don't know the right answer to this because I haven't done it yet, but I don't know the answer to that. this is not the real population. So this is the best we can do. So, what this is saying is the real answer you got really want to know is somewhere in between. It's the one the average works rate. And the question is, what is this? It's not the answer. The answer is somewhere here. We know that we need it. So, if we're saying this is our best guess, but we only check seven. If we check seven, that produces this error. So then I can say the right answer. It's like, look, real average is going to be. Because I'm trying to make sure I find this. So, what's stronger? I don't want to say it's really strong, but it's not. I want to say it's really weak. But and again, that doesn't mean this is better. This one. I'm just trying to promise something. This one, you get the comment at the top. And for example, oh, actually, the far whether somebody actually look at the answer, that doesn't make sense. Maybe one more minute, and then we'll do it together. It's huge, but why is it huge? That's why it's so huge. This number. I think that's right. Did you guys get the same thing? Check with your neighbor, see if you got the same thing, if you happen to be so close enough. They should be going, they should be taking. Adding the error. Those are the kind of things you should do. Right? All right, I'm catching up. So the error that I am going to be adding and subtracting to my sample of 2,100 pounds, my sample mean was 2,100 pounds. The error that I'm going to be adding and subtracting to that is what I need to know. That's the formula for it. I need the t-score, which is kind of like a z-score, and I need this sample standard deviation. That's the two things I need to get E. So what's that t-score? Inverse t, I put in the area. If this is 90, oops, I gotta zoom out. If I want to have a 98% confidence interval, then that means the area to the left of that would be 0.99. I hope you've practiced enough to know that. And then the second thing it wants is the degrees of freedom, which is always one less than this. So that's 6. So I got to come up with kind of a z-score. So what is that? Double check your work. Inverse t area point. Notice I want to be more accurate this time. 6 degrees of freedom, really small sample. So for that reason, I get a really big z-score. Remember, this still is standard deviations. That's saying like 3 standard deviations above the mean. That's still what that means. So this is approximately, again, I don't care how you rounded it, 3.14. Second ingredient I need is the sample standard deviation divided by the square root of n. My sample standard deviation was 133.3. My n was 7. Notice I'm not subtracting 1 from that. It just is n. The magic box says 133.3 divided by the square root of 7 is 50.38. 50.4, whatever, I don't care how you rounded it. So I can now find E. If I take 50.4 and multiply it by that z-score, I will get E. So my error, notice I have both of those numbers in my calculator. Why retype them when I already have them? Why not just say this number enter times this number enter? I got about, again, I don't care how you round, but because these are, you know, big numbers, I'm just going to call that 158. Close enough. And so now I can say that the actual right answer to the mean strength of these ropes, the mean population mean, is my sample 2,100 plus 158, my sample minus 158. So 2102 plus 158 minus 158, so 1944 to 2260. Again, on a test, I'm not splitting hairs. You don't need to have the exact answer I had, round however the heck you want. Just be reasonably close. 1944 to 2260. You should still be in process, but you should be getting close to understanding the importance of this and what this is. You have questions in your homework assignment that I'm going to grade where I ask you, what does that mean? And all of this is for nothing if you don't know what that means. So you got to work on that. You got to think about this. What does that mean? It means that good for you. You did a sample and broke 7 ropes and you got an average of 2,100 pounds. But that's not the average strength of the ropes. You only measured 7 of them. That is not the right answer. What is the right answer? Well, I'm 98% sure it's somewhere in here. Do you understand the difference? Do you understand what I'm saying? There's a 98% chance that it's somewhere in there. Remember, that still means there's a 2% chance it's not. Like, I still can't even be sure. As I said, we're never going to know the answer to this question. You cannot break every rope there is. So you're never going to know the answer to this, but we're going to still have to make a choice and bet people's lives on it. Do you understand how cool this is or how important this is, how powerful it is?
There's a question on the handed homework asking, based on your work in question 1, suggest the breaking strength you will publish. Would that be the mean between those two values?
No. And you couldn't have timed that better, because that's the next thing I want to talk about. So my point is, if you were saying, if you're going to talk about how strong your ropes are, would you want to say the average is 2102? The answer is no. What should you say based on this? That's exactly right. You should report that. Why? Because you want to tell people something that's actually true. Now, is that the right answer to the question? No, but what you're doing is making promises to people. You're saying, how much will this rope hold? If I said on average, it'll hold 1,944 pounds, that's a safe answer. It's not true, but remember, I'm just promising it will do a job. I'm saying it will hold something without breaking. And by the way, notice their answer, it's way below that. I want you to think about that a little bit. Now remember, if I report this as what? The mean breaking strength, which means half of your ropes are still going to break below that. Do you understand that? This is not the minimum breaking, this is not the breaking strength, it's the average breaking strength. Half the ropes are going to break over this, half the ropes are going to break less than that. This is just the middle. That's all I've established. So should I report this as the strength? No, because half your customers are going to sue you. Half of your customers will die if you say that. This is a mean. Question.
I'm so confused on how you get the 1944 and 2260.
Because I'm taking the sample 2102 and adding 158, the sample 2102 and subtracting 158.
So I'm sorry, can you repeat that? So you're taking the sample mean as the first part of the equation, and what is?
Yeah, this. Because this is the best answer I've got. It's not like this isn't part of the problem. I mean, I did do a sample, and this is the best answer I've got for the mean. It's just that I know it's wrong. And by adding to this an error of 158, then I can report a low number. And now this is my new better answer for the mean. If I'm going to report the mean now, I'm going to report this answer, because that's going to keep me from killing people. Does that make sense? I still don't know. I mean, for all I know, the answer is 2260. It's really strong. It's not like this one's more right than that one. It's just the lowest one on the list. I'm 98% sure that this is, well, I guess you could say I'm 98% sure it's above this. That feels reasonably safe.
So this is still the sample of that 1944, because I see the actual, this is going to be somewhere 1,486 pounds.
Yeah, now think about this. So as far as the second question, which Blake asked about on the test, on the hand-in homework, was basically the first question was do the same thing, wasn't it? Find a confidence interval. Yeah, do the same thing. And incidentally, just as a side note, notice there's actually 40 numbers there. That's a lot to type into your calculator. That's quite a few. You might actually screw that up. You have two choices there. You could carefully type all 40 of those in, but I also posted this in My Open Math as a Word document. And you could go in there and grab all 40 of those and paste them into Excel. So you don't have to type them, which saves time, and you're guaranteed not to screw it up. And let Excel do the calculations for you, which is what people would do in the real world, because Excel's easier. Everybody has it. And more importantly, you can actually make a report. Like you could actually show somebody, whereas you can't show people on your calculator, right? So feel free to do that. But I went on and asked another question, which is, what should you report like they did? They reported 1486 here as their promise. Like, our ropes are not going to break at less than that. That's their promise. Well, you remember the normal distribution. So where does 1944 go on the normal distribution? If it's the mean, then doesn't it go in the middle? Again, all we're doing, we're not saying that's the answer. We're just saying that's what we're going to use as the answer, because we don't want to be wrong. We're never going to know the actual population mean. We're just saying we're going to use that one because it's safer. Notice it dumped 150 pounds. Well, 158. We want 158 lower than our sample in a sense, just to be safe. That's what the confidence interval is about. I am not confident that this is the actual population mean. I am confident that the population mean is that or higher. You see the difference? And I didn't just make this up. I didn't just say, well, it's 2,100. How about if we just call it 1,000? Like, I actually did math. That's kind of cool. But if that's the mean, remember the purpose of this class. Isn't there standard deviations from the mean? As I said, isn't 50% of the ropes over here breaking below 1944? And isn't 50% up here breaking more than 1944? So where do you want to report? Well, wouldn't you be reporting a certain number of standard deviations away from the mean? Again, you're trying to be safe here. I don't want to give it away, but that's kind of the idea behind question 2 on the take-home homework. You're more than welcome to ask me questions about it. This is why I made it due not Sunday night, but Monday, so you can still ask me questions. I would really prefer you to show me your answer to number 2 before you just turn it in. There's not a particular right answer to this question. I don't have a number on my paper, and if you don't have that, you're wrong. But you should expect that's just the middle. You need to think about the fact that there's variation. Well, you saw it. Look, there's 40 ropes on your, well, in my case, there's 7 ropes here. There's a ton of variation there. Is every rope up here stronger than my answer down here? Look carefully at that. Is every rope up there stronger than that? No, there's one that's not. That's to be expected. Isn't there variation? So what should you report as your strength? And I'm not looking for you just to look at 1944 and go 1800, like just make it up. I'm looking for you to think of how many standard deviations away do you have to get away from the mean before you can start being confident. So think about that. What percent is within 1 standard deviation of the mean? What percent is within 2 standard deviations of the mean? Like, what should I report based on the whole purpose of this class? That's not an easy question. Like, I'm asking you to apply and think about everything we've learned in this class, and listening to me tell it to you once is not equal to you got it. So you should be, asking me questions about it. I'm going to shut up well before the class is over today, so you have time to ask me that. We've been talking for a long time. I think what I'll do is I'm going to show you one other quick thing, and we'll just be done. I could give you a break, but I just want to show you one quick thing, and we'll be finished. And my advice then would be to use that, start looking at your homework, or spend time with that hand in homework, or I can't stand it in here anymore. I got to get out of here. That's okay too. But the other thing we did. The other thing we did in the last section is what you should have noticed from these 2 examples is we had a lot of error. So I went by Megan and she was kind of thinking, did I do this wrong? Because I got an error of 158. That seems like a lot, she said. Yeah, that's huge. Why is it so huge? Well, the same reason as last time, which is you only checked with 7 ropes. Like, no wonder it's so huge. Does it make sense if this really mattered in the world? You might want to check with lots more. So what if you said, I don't want the error? What if you said ahead of time, I don't want an error of 158 pounds. I want an error of 10 pounds. I want to be accurate. I want to be a lot closer than 158. Well, this is kind of what we did in the last section. We said, well, God, we got an error of 20%. That's terrible. What would it take to get an error of 1%? And didn't we have a formula here, last section, where we said, okay, yeah, if you stick a z-score in there and that error you chose of 1%, then you could actually calculate what n was. Hopefully you've already done the 9.1 assignment and you're a little better at saying, yeah, I kind of understand that. Well, there's a formula for that in this section too. This formula. So I just want to stare at it with you a little bit and talk about it. So n is found, this formula says, by taking the z-score. That's weird, a z-score? I thought we were doing a t-score in this section. But what did it require to use a t-score just now? Let's look at the one we just did. What did you have to type in to use a t-score right there? That was n minus 1. In other words, you had to know what n was to even use it. Does that make sense? So you can't do an inverse t unless you know n, and we're trying to find n. So what did they do instead? Well, they said, let's not use that, let's use z. As I showed you, they're reasonably close to each other. If your n is a fairly high number, they're reasonably close. That's the best you can do. So the formula says take that number, multiply it by the sample standard deviation, and then divide that by whatever error you want, and square the whole thing, and that will tell you what n you should use. And again, I want you to appreciate that this is more realistic. In the real world, you don't just stupidly go say, oh, I think I'll just test 7 of them, only to discover after all that work that you have an error that's unacceptably high. Wouldn't it be better to say ahead of time, I would like an error of 10 pounds. 158 just seems crazy. I want an error of 10 pounds. I can live with an error of 10 pounds. Plus or minus 10 pounds, I think we're not going to kill anybody. That makes a lot of sense. And let's stick with, I don't know, let's ramp it up a little bit. Let's be 99% confident. This is a rope after all. We're going to kill people. We had 98 a second ago. Let's take it up to 99%. Well, as you know, we go inverse normal for a normal z-score distribution. And I type the area to the left. I haven't been drawing this today because I'm assuming you've got this down, but if the middle is 99%, then that only leaves 1% to share with both tails. So 1% cut in half would actually be 0.5% or 0.005. So I'm going to have to put in 0.995 and then 0 and 1. So I got a z-score of, again, I don't care how you round it, I'm going to call it 2.576. I don't know, whatever. So in the real world, you get to decide what size error you want. You can decide how confident you want to be. In the case of a rope, I want very small error. I want a really high confidence. And then what's the last thing that was calling for? What's the last ingredient of our recipe?
And sample deviation.
Yeah, a sample. Now that's the one thing about this that I think is kind of weird, because if we haven't started the experiment yet, wouldn't we not know that either? So we have to have some standard deviation value. So we either have to go look online and see if somebody has one somewhere that we could steal, or we would have to go perform a tiny one like we just did. We'd have to go get one. So your homework assignment, they're just going to tell you from some previous study, the standard deviation is 5 or whatever. They're going to tell you that. Let's just use the one I'm going to say here, sort of jokingly, from who knows where. Well, because I'm still thinking rope here, we'll use the one we already had. So it was 133.3. We did a previous study. We just decided once we got done that 158 was ridiculous. So we have a previous answer for this, 133. I'll leave the 0.3 in it. Okay, you got everything you need. What's your calculator say n should be then? You don't even have to know the order of operations. Just type all that stuff in there and say squared, and I'm doing it with you. parentheses, z-score 2.576 times S, 133.3 divided by E, which we said was going to be 10 pounds, close that parentheses, square it. Bam. I got N is approximately 1179.1.
You
Right.
would round that up, correct?
Yes, which needs to be technically, it's a very small technicality. You round up because you're saying I want an air that is 10 pounds or less. In other words, I don't want to be more than 10 pounds. If you just said I want the air to be around 10 pounds, then call it 1179, 1180, who cares? It's going to be around 10 pounds. But if you want 10 pounds or less, you want to make sure not to exceed an air of 10 pounds, then you gotta check with more ropes rather than less. As far as your homework assignment goes, these answers will always be, they'll always be rounded up. Even when, like in this case, it would round off to 1179, it's got to still be rounded up. Now, again, this is bad news, right? It's like, oh, you want to be accurate? Well, guess what? You got to go check with a lot of people. Like that should be expected. Now, that big, I mean, if I did that calculation, I might think, God, that's going to take me 3 weeks. Maybe I can live with 20 pounds of air. Like I'm going to go recalculate this, or maybe I don't need to be 99% confident. Maybe I can just be 96% confident. Like you can mess with stuff. But you can probably appreciate, they probably would not with the rope. Probably they would say, well, this is a life or death thing. So maybe even 99% confidence is not enough. But that'd be kind of cool if we redid this then. We're not going to redo this, but it'd be kind of cool if I redid it. And then I got, 2102 and it was only plus or minus 10 pounds. That'd be kind of cool. But of course, if I did redo this with 1180 of them, I probably am not going to get the same answer here, right? Because remember, there might be one weird one. Is there one weird one here? These two, this one's pretty weird low. 2272 is pretty high, but then notice there's a 2200. It doesn't feel like there's an outlier here. But you can appreciate if I did this with 1180 ropes, that whatever answer I get for this, I'm going to sure feel more solid with it, right? And that's the idea. Whatever answer I get, I'm only going to have to go up or down 10, and I can say the answer's in that range somewhere. That's kind of cool. All right, how's your brain? Pain? My brain is in pain. I didn't understand this in one pass. I survived it in one pass, but I didn't understand it in one pass. Cut yourself a little slack. Okay, do what you want now with the time. If you want to ask me homework questions, do it. If you just need to get away, do that.